Measure a particle's position precisely enough, and you lose all certainty about its speed. Measure its speed precisely, and you lose its position. This is not a limitation of our instruments. It is not a flaw in our methods. It is a fundamental property of nature itself, written into the fabric of reality at the deepest level we have ever probed. Most of what we take for granted about the world rests on a hidden assumption that things exist whether or not we look at them. A chair in an empty room is still a chair. A planet on the far side of the sun still has a mass, a position, a velocity. This assumption is so deeply embedded in how humans think that questioning it feels absurd. But quantum mechanics, the most rigorously tested and precisely accurate theory in the history of science, does exactly that. It forces the question, and the answer it gives is genuinely unsettling. Before we dive deeper into this, just one small thing. I don't want millions of random viewers. I want a small group of people who truly connect with what I'm creating. If you feel that connection even a little, consider subscribing. Let's build something meaningful here. Alright, now let's continue. For most of human history, the search for the building blocks of matter looked straightforward. Ancient Greek philosophers proposed that everything in the universe was made of combinations of a few fundamental substances: earth, air, fire, and water. This was a serious intellectual attempt, a rational effort to explain the complexity of the natural world through simplicity. They were wrong about the specifics, but the instinct was sound. Over 2,000 years later, chemists and physicists confirmed that matter really does reduce down to a limited set of fundamental components. By the early 20th century, the atom had been confirmed as real, and for a brief moment, it seemed like the picture was complete. Matter was made of atoms. Atoms were the bottom. Then came the experiments. Researchers like Max Planck, Albert Einstein, and Niels Bohr began probing atomic behavior in the late 1800s and early 1900s. What they found dismantled the comfortable Newtonian picture of the universe. Atoms were not solid little balls. They had internal structure. They contained even smaller components, electrons orbiting a nucleus packed with protons and neutrons. And these smaller particles did not behave like anything anyone had encountered before. They did not follow the predictable trajectories of cannonballs or planets. They exhibited behaviors that had no analogue in the everyday world. They seemed to exist in multiple states at once. They seemed to respond to the act of measurement itself. Today, the standard model of particle physics represents humanity's best account of what matter and energy are made of at the smallest accessible scales. According to this framework, the fundamental building blocks are not atoms but subatomic particles, electrons, quarks, neutrinos, and several others. Protons and neutrons, which form the nuclei of atoms, are themselves composed of quarks bound together by particles called gluons. The electron, as far as we can determine, has no internal structure at all. It appears to be genuinely elementary, but even this picture does not capture the full depth of what quantum theory reveals. Quantum field theory, the synthesis of quantum mechanics and special relativity, describes particles not as tiny solid objects, but as localized disturbances in underlying fields that permeate all of space. An electron is not a small ball. It is a ripple in the electron field. A photon is a ripple in the electromagnetic field. Every type of particle corresponds to a field that exists everywhere in the universe. What we call particles are simply the excited states of those fields. The universe, in this picture, is not a collection of objects moving through empty space. It is a vast collection of overlapping, interacting fields, and what we experience as matter and light and force are simply the ways those fields vibrate and interact. This is already strange, but the quantum part of quantum field theory is what truly breaks our intuitions. In classical physics, a system has a definite state at every moment in time. An object has a specific position. It has a specific momentum. These properties are real and objective, existing independently of anyone looking at them. If you want to know them, you measure them. Measurement reveals the pre-existing values. The map corresponds to the territory. In quantum mechanics, this is not how things work. Before a measurement is made, a quantum system does not have definite values for all of its properties. Instead, it exists in what physicists call a superposition of states. The particle is not in one place with one momentum. It is in a combination of many possible positions and many possible momenta simultaneously. The wave function, a mathematical object at the heart of quantum theory, does not describe where the particle is. It describes a distribution of probabilities for where the particle might be found if you were to look. And here is where it gets genuinely strange. When you do look, when you make a measurement, the wave function does not simply reveal the pre-existing position. The act of measurement appears to cause the system to suddenly settle into a single definite state. The superposition collapses. This process is called wave function collapse, and it is one of the most contested and debated phenomena in the whole of physics. Before measurement, many possibilities. After measurement, one outcome. What happens in between? Nobody knows. And physicists disagree sharply about what, if anything, is physically real about the wave function itself. In 1935, the physicist Erwin Schrödinger devised a thought experiment that has since become one of the most famous in all of science. He imagined placing a cat inside a sealed box. Inside the box, alongside the cat, is a vial of poison connected to a mechanism triggered by the radioactive decay of a single atom. Radioactive decay is a genuinely quantum process. According to quantum mechanics, before any measurement is made, the atom exists in a superposition of having decayed and not having decayed. If the atom is in that superposition, and if the cat's fate is linked to the atom's state, then the cat too must be in a superposition, both alive and dead simultaneously. Schrödinger did not present this as a demonstration of something wonderful. He presented it as a reductio ad absurdum, a demonstration that something must be wrong with the naive interpretation of quantum mechanics. The idea that a macroscopic object, like a cat, could genuinely be in two contradictory states at once struck him as physically absurd. The thought experiment was meant to highlight a problem, but here is the disconcerting thing. Physicists have never fully resolved the problem Schrödinger was pointing at. We have learned a great deal about why macroscopic superpositions are extremely difficult to maintain. A process called decoherence explains why large objects made of many atoms rapidly lose their quantum character through interactions with the environment. But decoherence is not the same as collapse. It explains why we cannot observe superpositions in everyday objects. It does not fully explain why a measurement produces one outcome rather than many, or what is really happening to the wave function when it appears to collapse. To understand what is at stake here, consider the Heisenberg uncertainty principle. This is not, as it is sometimes misunderstood, a statement about the clumsiness of our measurements. It is not saying that when we measure a particle's position, we inevitably disturb its momentum with our instruments. The uncertainty principle is a statement about the nature of the particle itself. Position and momentum are not both well-defined properties that a particle possesses before we look. They are complementary quantities, linked by the structure of quantum mechanics in such a way that the more precisely one is defined, the less precisely the other can be. This is a mathematical consequence of the wave nature of quantum systems. It is built into reality at a fundamental level. The same applies to other pairs of complementary properties. Energy and time spin in different directions, and others. In each case, the universe itself imposes a limit on how precisely both quantities can simultaneously exist, not just be measured, exist. This leads to one of the most counterintuitive conclusions in all of science. The question of what a particle's properties are when no one is looking may not have a well-defined answer. The universe does not maintain a complete ledger of all physical quantities at all times. Some properties, it seems, are genuinely created in the act of measurement rather than revealed by it. This unsettling conclusion is formalized in what is called the Copenhagen interpretation of quantum mechanics, developed primarily by Niels Bohr and Werner Heisenberg in the 1920s. According to this view, quantum mechanics is a theory about the results of measurements. It tells us, with extraordinary precision, what outcomes we will observe and with what probabilities. It does not and should not, in Bohr's view, make claims about what is happening to quantum systems when they are not being observed. The wave function is a calculational tool, not a description of physical reality. Questions about what particles are doing between measurements are, in this view, meaningless. Not unanswered, meaningless. Many working physicists, perhaps the majority, have adopted some version of this pragmatic stance. The calculations work. The predictions are accurate to a degree unmatched anywhere else in science. Quantum electrodynamics, the quantum theory of electrons and photons, makes predictions that have been tested to 1 part in 10 billion and found to be correct. From this standpoint, asking what the wave function really means is like asking what a weather forecast really means. It is a tool. It works. Stop worrying. But a substantial number of physicists and philosophers find this position deeply unsatisfying. Science has always aspired to more than prediction. It has aspired to understanding. A theory that can predict every measurement, result with arbitrary precision, but cannot tell us what is actually happening to the physical world between measurements, seems to leave something important out. The question of interpretation is not just philosophical decoration. It touches on the deepest questions about the nature of reality. The main alternative interpretations of quantum mechanics each try to restore something that the Copenhagen interpretation abandons, either a definite physical reality or a definite causal story about how events unfold. The many worlds interpretation, first proposed by Hugh Everett in 1957, takes the wave function completely seriously as a description of physical reality and refuses to accept collapse as a physical process. Instead, every time a measurement occurs, the universe branches. Every possible outcome happens. In some branches of the wave function, the cat in Schrödinger's box is alive. In others, it is dead. Both branches are equally real. The reason we observe only one outcome is not that the other possibilities disappear. It is that we ourselves are part of the wave function. We too branch. Each version of us sees only its own branch. The universe in this picture is not a single history. It is a vast, constantly branching structure containing every possible history, all equally real. The many worlds interpretation has the considerable virtue of taking quantum mechanics at face value, with no additional collapse mechanism, no special role for observers, no discontinuous jump from superposition to single outcome. The mathematics is clean, but the ontological cost is enormous. It requires accepting the literal existence of an incomprehensible number of parallel universes, more branches than atoms in the observable universe, generated continuously by every quantum event everywhere. Another approach is the pilot wave theory, also known as Bohmian mechanics, developed by Louis de Broglie and later revived and expanded by David Bohm. In this interpretation, particles always have definite positions. The apparent randomness and uncertainty in quantum mechanics are real, but they arise from our ignorance of the precise initial conditions rather than from any fundamental indeterminacy in nature. Particles are guided by a real physical wave, the pilot wave that navigates them through space. The wave follows the Schrödinger equation exactly. The particle follows the wave. Crucially, this theory is non-local. The pilot wave for any particle depends on the state of all other particles in the universe simultaneously, regardless of how far apart they are. This non-locality is the price paid for restoring determinism and definite particle positions. Then there are relational interpretations, information theoretic interpretations, and cubism, which treats quantum mechanics as a theory about the beliefs and expectations of agents, not about the world independently of those agents. Each of these frameworks makes the same experimental predictions as standard quantum mechanics. Each is, in the technical language of physics, empirically adequate, and none of them can be distinguished from the others by any experiment we know how to perform. This situation is deeply unusual in science. Normally, competing theories make different predictions, and experiments decide between them. Here, the competing interpretations are not theories in the usual sense. They are metaphysical frameworks layered on top of the same mathematical structure. They agree on all the numbers. They disagree about what those numbers mean. The question of which interpretation is correct is not, in the current state of science, an empirical question. It is a question about what kind of reality we are willing to accept, and different physicists and philosophers find different answers acceptable. What makes this more than idle philosophical debate is the question of what quantum mechanics says about the nature of physical reality in general. Because quantum mechanics is not just a theory of atoms and particles, it is, as far as we can tell, a theory of everything. Every interaction in the universe is fundamentally quantum mechanical. Chemistry is quantum mechanics. Radioactivity is quantum mechanics. The fusion reactions that power stars are quantum mechanics. The electrical signals in your nervous system depend on the quantum mechanical behavior of ions and molecules. If quantum mechanics is strange and hard to interpret, it is strange and hard to interpret at every level of reality. One of the most striking illustrations of quantum weirdness is the phenomenon of quantum entanglement. When two particles interact under the right conditions, their quantum states can become correlated in a way that has no classical analogue. The two particles become entangled. After that, the quantum state of the combined system cannot be described independently for each particle. The particles form a single quantum system, regardless of how far apart they subsequently travel. If you then measure a property of one of the entangled particles, you immediately know something about the corresponding property of the other particle, no matter how far away it is. The correlations are instantaneous. They do not diminish with distance. And they are not merely correlations that existed from the beginning, encoded in the particles' states when they were created. This was proved experimentally through a series of increasingly refined tests of what are called Bell inequalities. In the 1960s, the physicist John Bell derived a mathematical theorem showing that if the world is locally realistic, meaning if the properties of particles are determined before measurement and cannot be influenced by events at distant locations faster than light, then any correlations between measurement results must satisfy certain mathematical bounds, the Bell inequalities. Quantum mechanics predicts that entangled particles will violate these bounds, and experiments have confirmed with overwhelming statistical confidence that the violations occur exactly as quantum mechanics predicts. This result has profound implications. It rules out any theory of reality in which particles have pre-existing, locally determined properties. The correlations between entangled particles cannot be explained by any hidden variables that the particles carried from their creation. The universe is not locally realistic. Either the particles did not have definite properties before measurement, or the properties of a particle at one location can be instantaneously influenced by what happens to a distant particle, or both. No local, realistic, classical account of the universe is possible. This does not mean that information can be transmitted faster than light through entanglement. No signal can be sent using quantum correlations, because the individual measurement results on each side are random. The correlations only become apparent when the two sides compare their results, which requires ordinary, slower-than-light communication. But the correlations themselves are non-local in a way that has no classical explanation. The universe, at a fundamental level, is not made of locally interacting, independently existing pieces. Whatever quantum reality is, it cannot be fully decomposed into separate parts with separate properties. This aspect of quantum mechanics troubled Einstein deeply. He accepted the experimental evidence, of course, but he believed the theory was incomplete. Somewhere, he thought, there must be hidden variables, pre-existing properties that quantum mechanics fails to capture, but that a more complete theory would reveal. The entanglement correlations, in his view, were not a sign of genuine non-locality, but of missing information. Bell's theorem closed that door. Hidden variables that are both local and real cannot explain what is observed. Einstein's intuition about a deeper, more complete reality was not wrong in principle, but the universe simply does not appear to accommodate it. The wave-particle duality of quantum systems is another feature that resists any simple classical interpretation. In the famous double-slit experiment, a single particle, an electron or a photon, is fired at a barrier with two narrow openings. If you do not attempt to measure which slit the particle passes through, an interference pattern builds up on the detector screen behind the barrier. The particle behaves as if it passed through both slits simultaneously and interfered with itself. This is wave behavior, not particle behavior. But if you place a detector at one of the slits to determine which path the particle actually took, the interference pattern disappears. The particle behaves like a particle. The act of gaining information about the path destroys the wave-like behavior. This is not a technological limitation. It is not that our particle detectors are too crude. It is a fundamental feature of the quantum world. Gaining information about a quantum system necessarily alters its behavior. The universe does not allow you to simultaneously know which path a particle took and observe the wave interference that results from it not taking a definite path. These are mutually exclusive possibilities, not just practically but in principle. The minimal mathematical requirements to fully describe a quantum particle are surprisingly few. Mass, charge, and spin, a form of angular momentum with no classical analogue, are sufficient to fully characterize a fundamental particle. From these properties and the Schrödinger equation, you can derive the particle's wave function, and from the wave function, you can calculate the probability of any possible measurement outcome. The wave function is not a description of where the particle is. It is a description of what you will find when you look across all possible measurements you might make. It contains everything that can be known about the particle's quantum state, and it says nothing about what the particle is doing when no one is looking. The question of what causes wave function collapse, what counts as a measurement, and what role, if any, consciousness plays in quantum mechanics has been debated since the founding of the theory. Some of the founders, particularly John von Neumann and Eugene Wigner, took seriously the possibility that consciousness is essential. In their view, the chain of physical interactions that constitutes a measurement has no definite outcome until it registers in a conscious mind. This is a minority view, and most physicists do not accept it. But it has never been definitively ruled out, because the boundary between measurement and non-measurement, between quantum superposition and definite classical outcome, has never been precisely defined within quantum mechanics itself. The Decoherence research program, which flourished in the 1980s and 1990s, made important progress on this question. When a quantum system interacts with its environment, which consists of countless other quantum systems, information about the quantum system's state rapidly spreads into the environment. This process of entanglement with the environment effectively destroys the coherence of superpositions from the perspective of any local observer. The system behaves, for all practical purposes, as if it had collapsed into a definite classical state. Decoherence explains why Schrödinger's cat states are never observed in practice for large objects. The rate of decoherence scales with the size of the system, and for macroscopic objects it is so fast as to be unmeasurable. A cat-sized superposition would decohere in a time far shorter than any physical process we could use to detect it. But decoherence, as its practitioners are careful to note, does not solve the measurement problem completely. It explains why we cannot observe macroscopic superpositions. It does not explain why we observe one specific outcome rather than another. After decoherence, the combined quantum state of system plus environment still contains all the possible outcomes, each entangled with a different state of the environment. Something still has to select one outcome. Decoherence shows that this selection problem does not arise from the environment's interference with our measurements. It does not eliminate the problem. The research frontier on Schrödinger cat states has moved from thought experiments to laboratory reality. In recent decades, physicists have successfully created superposition states involving increasing numbers of particles and atoms. Experiments with superconducting circuits, trapped ions, and cold atomic gases have produced superpositions of macroscopic electrical currents flowing simultaneously in opposite directions. Superpositions involving millions of atoms, and quantum states of mechanical resonators visible to the naked eye. These experiments are probing the transition between the quantum and classical worlds in ways that were unimaginable even 30 years ago. These quantum systems are not merely scientific curiosities, they are the basis for an emerging technological revolution. Quantum computers exploit superposition and entanglement to process information in fundamentally new ways. For certain computational problems, quantum algorithms can outperform any classical algorithm by an exponential factor. Quantum cryptography uses the fundamental unpredictability of quantum measurement to create encryption schemes that are in principle unbreakable by any physical means. Quantum sensing exploits the extreme sensitivity of quantum systems to their environment, creating instruments of extraordinary precision for measuring magnetic fields, gravitational fields, and time. Understanding the quantum world more deeply is not an abstract academic pursuit. It has direct technological consequences, and the degree to which we can extract useful information from quantum systems and the degree to which we can maintain coherent quantum states against decoherence depends on understanding the physics of measurement, entanglement, and quantum state evolution at a deep level. There is a question that sits beneath all of this, rarely stated explicitly in physics papers, but impossible to avoid. What does quantum mechanics tell us about the nature of reality itself? The answer, uncomfortable as it is, seems to be that the concept of an observer-independent, fully determinate, locally real physical world is not supported by the evidence. Not because our technology is insufficient, not because our theories are incomplete, but because quantum mechanics, the most successful physical theory ever devised, is inconsistent with a classical picture of reality, and every attempt to restore that picture while maintaining agreement with experiment has required either accepting non-locality, accepting the existence of infinitely many parallel universes, or accepting that the theory says nothing about reality between measurements. Some physicists are comfortable with each of these options. Others remain convinced that something important is still missing, that a future theory will resolve the tensions in a way that current quantum mechanics cannot. The history of physics offers some support for both positions. The transition from classical mechanics to quantum mechanics involved accepting genuine conceptual discontinuity. There was no smooth path from Newton to Schrödinger. Future theories may well require an equally radical reconceptualization of what we currently understand. But there is something important to hold on to here. even amid all this uncertainty, quantum mechanics works. It works with a degree of precision that no other physical theory has ever achieved. Its predictions have been tested against experiment millions of times, across every domain, from atomic physics to cosmology to condensed matter, and it has never been found wrong. The weirdness is not a defect in the theory. It is what the universe is telling us when we ask the right questions. Physics is not troubled by reality seeming strange. It is only troubled if we demand that reality conform to our intuitions rather than to what experiments reveal. The quantum world does not behave like a scaled-down version of the everyday world. It behaves like itself. And learning to accept that, to let go of the assumption that the universe must ultimately make sense in terms of billiard balls and clockwork mechanisms, is perhaps the most important conceptual shift that modern physics requires of us. What we can say with confidence is this: reality, at its most fundamental level, is probabilistic, non-local, and contextual. Properties of quantum systems are not always defined before they are measured. Distant quantum systems can be correlated in ways that cannot be explained by any local mechanism. And the act of measurement is not a passive revelation of pre-existing facts, but an active interaction that is woven into the fabric of what those facts are. These are not interpretations or philosophies. They are the direct experimental conclusions of a century of careful, precise, reproducible scientific work. The universe has been answering our questions consistently and clearly. What remains unsettled is what those answers mean about the world that was there before we started asking. The research being done today on quantum systems is pushing further into this unsettled territory. Experiments testing Bell inequalities have been refined to close increasingly subtle potential loopholes, most recently in what physicists call loophole-free Bell tests. The results continue to confirm quantum predictions. Experiments with larger and larger quantum superpositions are probing where, if anywhere, the quantum to classical transition occurs. And theoretical work on quantum gravity and the quantum origins of spacetime is attempting to understand whether the geometry of the universe itself has quantum properties. There is also growing interest in quantum biology, the question of whether quantum effects play a role in biological processes. Evidence has emerged that photosynthesis in plants exploits quantum coherence to transfer energy with near-perfect efficiency. The navigation of migratory birds may depend on quantum entanglement in chemical reactions in the eye. These findings suggest that the quantum world is not merely a microscopic curiosity, but a fundamental contributor to the organization of living systems. What scientists do not yet understand is where the quantum world ends and the classical world begins, or whether that boundary is sharp at all. They do not know whether quantum mechanics is the final theory at its scale, or whether it will eventually be subsumed into a deeper framework. They do not know whether the wave function is a real physical object, a useful calculational fiction, or something that points to a reality for which we do not yet have language. What they do know is that quantum mechanics describes the world as it actually is, not as we would like it to be. Every time an experiment has been run, every time a precision measurement has been made, the universe has confirmed the quantum picture. The challenge now is not to make quantum mechanics work. It already works. The challenge is to understand what it means and to develop the experimental tools to test between the philosophical possibilities that its mathematics leaves open. Until then, the most honest thing that can be said is this: at the deepest accessible level, the world is genuinely strange. Not strange in a superficial sense, not simply unfamiliar. Strange in the sense that the assumptions which have guided human thinking about reality for all of recorded history turn out not to apply. The universe is under no obligation to be simple. It is under no obligation to be intuitive. It has shown us what it is, in precise quantitative detail. And what it has shown us is that the map we thought we understood was drawn for a different territory. If you find yourself returning to questions like these, to the structure of quantum reality, to the nature of matter and measurement, to the deep puzzles at the foundation of physics, then staying with this kind of material is worth your time. There is always more to explore. Liking this video helps others find it, and subscribing means you will be there when the next layer is peeled back. The physicists working on these questions today are not confused about the calculations. They are not uncertain about the predictions. What they are working through is something harder, understanding what it means for reality itself to be fundamentally quantum. And the most important thing about that work is that it is not finished. To appreciate how radical quantum mechanics truly is, it helps to understand what came before it and why the transition was so intellectually violent. Classical physics, the physics of Newton and Maxwell and Faraday, was built on a picture of the world that seemed not just plausible, but inevitable. Objects had positions, they had velocities. Given exact knowledge of all positions and velocities at one moment, a sufficiently powerful calculator could in principle predict every future state of the universe. The universe was a deterministic machine, elegant in its logic, predictable in its operation. Cause flowed smoothly into effect. The future was written, if only one could read fast enough. Pierre-Simon Laplace, the French mathematician and physicist writing in the early 19th century, gave this worldview its most vivid formulation. He imagined an intellect that knew the position and velocity of every particle in the universe at some single instant. For such an intellect, he wrote, nothing would be uncertain, and the future, like the past, would be present to its eyes. This image of a clockwork cosmos, fully determined and in principle fully knowable, was the philosophical backdrop against which the founders of quantum mechanics had to work. And it was not merely a convenient assumption. By the end of the 19th century, classical physics had accumulated an extraordinary track record of success. It explained the orbits of planets, the behavior of gases, the propagation of light, the operation of engines, the flow of electricity. It seemed, to many at the time, nearly complete. Then came a series of experimental results that could not be explained. The first came from the study of thermal radiation, the light emitted by hot objects. A metal rod, heated to incandescence, glows red, then orange, then white as it gets hotter. The distribution of colors in this light, the precise mixture of wavelengths emitted at each temperature, was a problem that classical physics could not solve. Its predictions diverged catastrophically from measurement at short wavelengths, producing nonsensical infinities. This failure was so stark that physicists called it the ultraviolet catastrophe. Max Planck found a mathematical formula that correctly described the observed radiation spectrum, but the formula required a strange assumption, that energy could only be emitted or absorbed in discrete packets, what he called quanta. The size of each quantum was proportional to the frequency of the radiation, linked by a constant now known as Planck's constant. Planck himself did not initially believe this quantization was physically real. He thought it was a mathematical trick. He was wrong in his modesty. The quantization was real. Albert Einstein extended this idea in 1905 in a paper that would eventually win him the Nobel Prize, though it was not the paper about relativity. Einstein proposed that light itself was composed of discrete packets of energy, what we now call photons. This was the explanation for the photoelectric effect, the observation that shining light on metal can eject electrons, but only if the light is above a certain frequency, regardless of its intensity. Classical physics predicted that increasing the brightness of light should always eventually eject electrons. Experiments showed this was not the case. Only light above a certain frequency would work, no matter how dim, and below that frequency, no amount of brightness made any difference. Einstein's photon picture explained this perfectly. Each photon either had enough energy to eject an electron, or it did not, and the energy of each photon depended on its frequency, not on the total brightness. This was a direct challenge to the wave theory of light, which had been extraordinarily successful for over a century. James Clerk Maxwell's equations, developed in the 1860s, had unified electricity and magnetism and predicted the existence of electromagnetic waves. Light was electromagnetic radiation. It was a wave. The mathematics said so, and interference experiments had confirmed it beautifully. Waves do not come in discrete packets. They are continuous. And yet the photoelectric effect showed that when light interacted with electrons, it behaved as though it were made of particles. Both things seemed true simultaneously, and they seemed to contradict each other. This was wave-particle duality making its first appearance, not as a philosophical notion, but as an experimental fact. Niels Bohr added another piece in 1913 with his model of the hydrogen atom. The electron in a hydrogen atom, he proposed, could only occupy certain specific orbits with specific energies. It could not exist at intermediate energies. When it jumped from a higher energy orbit to a lower one, it emitted a photon with an energy exactly equal to the energy difference. This explained the discrete spectral lines of hydrogen, the precise set of colors that hydrogen gas emits when energized, which had been measured but not explained since the mid-19th century. Bohr's model worked, for hydrogen at least, but it had no theoretical justification. Why could the electron only occupy specific orbits? Nobody knew. The answer came with the development of quantum mechanics in the 1920s, primarily through the work of Werner Heisenberg, Erwin Schrödinger, Paul Dirac, and Max Born. In 1925, Heisenberg reformulated atomic physics in terms of matrices, mathematical arrays of numbers that represented observable quantities. His formulation made correct predictions, but was difficult to interpret physically. The following year, Schrödinger independently developed what seemed like a completely different approach, using a wave equation. The Schrödinger equation described the time evolution of a wave function, a mathematical object associated with each quantum system. Schrödinger believed his wave function represented a real physical wave, a continuous, spread-out entity. Max Born showed that this interpretation was wrong and proposed the one that has survived. The wave function, Born argued, is not a physical wave in the same sense as a water wave or a sound wave. Its square, at any point, gives the probability of finding the particle at that point if you were to make a measurement. The wave function is a probability amplitude. It is a prescription for calculating the odds of different outcomes. Physical reality, in this interpretation, is probabilistic at a fundamental level. This probabilistic interpretation was what Einstein famously rejected with his remark that God does not play dice. He was not being superstitious. He was expressing a deeply held philosophical conviction that a complete physical theory must be deterministic, that probabilities in physics must ultimately reflect ignorance of hidden underlying facts, not genuine randomness in nature. He spent the rest of his life searching for alternatives. The experiments have since confirmed, through Bell test after Bell test, that his intuition, in this case, was not borne out by the universe. Heisenberg and Schrödinger's approaches turned out to be mathematically equivalent, different representations of the same underlying structure. Paul Dirac unified them into a more general formalism that remains the foundation of quantum mechanics to this day. And Dirac did something else extraordinary. He combined the Schrödinger equation with special relativity to produce the Dirac equation, a relativistic quantum equation for the electron. The Dirac equation automatically predicted that the electron must have spin, a property that had been discovered experimentally but had been inserted into quantum mechanics by hand. More dramatically, the Dirac equation required the existence of antiparticles, particles identical to known particles but with opposite electric charge. The positron, the antiparticle of the electron, was discovered experimentally in 1932, exactly as Dirac's equation predicted. This was one of the most stunning theoretical predictions ever confirmed in the history of physics. The confirmation of antimatter was also, in a sense, a confirmation of quantum field theory. because the Dirac equation is not just a relativistic quantum equation for particles. It is naturally interpreted as describing fields whose excitations are particles and antiparticles. Quantum field theory grew from this insight. It is the framework in which quantum mechanics and special relativity are properly unified, and it describes all the fundamental forces and particles we know of, with one exception: gravity. General relativity, Einstein's theory of gravity, describes gravity as the curvature of spacetime produced by mass and energy. It is formulated in entirely classical terms. There is no quantum version of general relativity that works the way quantum field theories work for the other forces. Attempts to quantize gravity in the straightforward way, by treating the gravitational field as another quantum field, run into severe mathematical difficulties. The calculations produce infinities that cannot be removed by the standard techniques that work for quantum electrodynamics. Quantum gravity remains one of the deepest unsolved problems in theoretical physics. This is not merely a technical puzzle, it is a fundamental conceptual problem. Quantum mechanics requires a fixed background spacetime, a stage on which quantum events occur. General relativity says that spacetime is not a fixed background, but a dynamic entity that responds to the matter and energy within it. These two pictures do not fit together easily. At the scales where both quantum effects and gravitational effects are important simultaneously, which are scales a billion times smaller than an atomic nucleus, called the Planck scale, we simply do not know what happens. We have no theory that works there. String theory and loop quantum gravity are the two most developed approaches to quantum gravity, and both propose radically new pictures of spacetime at the Planck scale. String theory replaces point particles with one-dimensional strings vibrating in 10 or 11 dimensions, most of which are curled up too small to observe. Loop quantum gravity proposes that space itself is quantized, composed of discrete chunks with a minimum possible volume. Neither theory has yet made predictions that have been confirmed experimentally, which means that as of now, we cannot tell which, if either, is correct. The questions surrounding quantum gravity are not separate from the interpretation questions we discussed earlier. They are deeply related. If spacetime itself is quantized, then the notion of a classical spacetime background on which quantum fields evolve is an approximation that breaks down at small scales. The wave function of the universe, if there is such a thing, would be a quantum state that includes both matter and geometry. There would be no fixed stage. The measurement problem would not just be a puzzle about particles. It would be a puzzle about the very structure of space and time. This is the frontier, and it is genuinely open. No one knows the answer. Returning to the domain where quantum mechanics is well established and tested, one of the most conceptually illuminating experiments in quantum physics is the delayed choice experiment, first proposed by John Archibald Wheeler in the 1970s and carried out experimentally in subsequent decades. The setup is a variation of the double-slit experiment. In Wheeler's version, the decision about whether to measure which path the particle took is made after the particle has already passed through the slits, but before it hits the detector. The question is whether this after-the-fact decision can affect whether the particle shows wave-like or particle-like behavior. The answer is yes. If the experimenter chooses to which path measurement mode, the particle behaves as if it took a definite path, even though that decision was not made until after the particle had already passed the slits. If the experimenter chooses to look for interference, the particle shows the wave pattern as if it had passed through both slits simultaneously. Wheeler interpreted this as showing that the past behavior of the particle is not fixed until a measurement is made in the present. The particle does not secretly take one path while we are not looking, waiting for the measurement to reveal which one. The particle's history is, in some sense, determined by our present choices. He described this as the participatory universe, the idea that observers, through their choices of what to measure, play a constitutive role in the reality they observe. This is a deeply unusual concept. It suggests that the history of the universe is not simply a record of events that happened independently of being observed. At the quantum level, what happened in the past depends, in a well-defined mathematical sense, on what measurements are made in the present. This does not mean that the past can be changed in any ordinary sense. No information travels backward in time. No causal order is violated. But the quantum mechanical account of the past, the wave function at earlier times, is not fully determined until measurements are made later. Wheeler extended this line of thinking into cosmology. He imagined placing the double-slit apparatus at cosmological distances, using gravitational lensing by distant galaxies to create two paths for photons that have been traveling for billions of years. A photon emitted by a quasar billions of light years away could have its path bent by an intervening galaxy along two different routes. If we choose to detect which route the photon took, we force it to have traveled one definite path, a path it was on for billions of years before any human existed. If we choose to observe interference, we confirm that the photon took both paths simultaneously for the entire duration of its journey. Wheeler believed this showed something profound, that observers are not merely passive spectators of a universe that would have been just as real without them. Observation is constitutive of reality at the quantum level. He did not mean by this that human consciousness creates reality in some mystical sense. He meant that quantum mechanics, taken at face value, implies that the properties of physical systems are genuinely contextual, defined relative to interactions and measurements, rather than existing absolutely independently of them. This point connects back to the Bell inequality experiments and what they established. The impossibility of a local, realistic, hidden variable theory means that no account of reality in which all properties are predetermined and locally defined is consistent with experiment. Whatever quantum reality is, it is not like that. Properties are not just unknown to us before measurement. They are, in some sense, genuinely not there before measurement, at least not in the form they take after measurement. This conclusion was so disturbing to so many physicists that it prompted a long series of attempts to find loopholes in Bell's theorem, ways to restore some version of local realism while still agreeing with experiment. One by one, these loopholes have been closed. The freedom of choice loophole, the idea that the measurement settings might not be truly independent of the particle properties, was addressed in a remarkable experiment that used the polarization of photons from distant stars as random number generators. The measurement settings were determined by signals that had left their sources thousands of years before the experiment, making any common cause explanation extraordinarily implausible. The results still confirmed quantum mechanics. The detection loophole, which concerned whether detectors with less than perfect efficiency might introduce statistical bias, was closed in experiments using entangled ions with near-perfect detection efficiency. The locality loophole, which required that the measurement settings be chosen and the results recorded while the two particles were separated by a space-like interval, preventing any light-speed signal from connecting them, was also addressed in multiple experiments. In a landmark experiment in 2015, physicists closed all the main loopholes simultaneously for the first time in what became known as a loophole-free Bell test. The results confirmed, with 5 sigma statistical confidence, that the quantum predictions hold even in the most stringent conditions. 5 sigma confidence is the standard for claiming a discovery in particle physics. It means the probability that the result is a statistical fluke is less than 1 in 3.5 million. The loophole-free Bell tests achieve this level of confidence while ruling out any locally realistic description of nature. This is one of the most consequential experimental results in the history of physics, and it received considerably less public attention than it deserved. What it established is that the universe is not locally realistic. This is not a philosophical preference or an interpretation issue. It is an experimental fact. Either the outcomes of quantum measurements are not determined by local hidden variables, or there exist influences that propagate faster than light. Since special relativity is extraordinarily well established, and since we know quantum entanglement cannot be used to send information faster than light, the most coherent conclusion is that quantum events genuinely do not have predetermined outcomes. The randomness is real. The universe truly does play dice, at least at the quantum level. Understanding why this is the case, rather than merely documenting that it is the case, is what the interpretation debates are ultimately about. And here, honest scientists must admit, we do not know. We have a theory of extraordinary power and precision. We have experimental results of extraordinary clarity. What we do not have is a consensus on what these results reveal about the deep structure of reality. There is another thread worth following here, one that connects quantum mechanics to information theory in a way that has become increasingly important over the past few decades. In the 1990s and 2000s, a new way of thinking about quantum mechanics emerged from the study of quantum information and quantum computing. In this view, the central object of quantum mechanics is not the wave function of a particle in space, but the information content of a quantum system, its capacity to encode, store, and transform information. The wave function is reconceived as a representation of an agent's information about a system, not a description of an objective physical state. This view, associated with approaches like cubism and relational quantum mechanics, relocates the puzzle of quantum mechanics from physics to epistemology. The question is not what the wave function is, but what it represents from the perspective of an agent performing measurements. In relational quantum mechanics, developed by Carlo Rovelli, the state of a quantum system is not absolute. It is relative to a particular observer or measuring device. Different observers can assign different quantum states to the same system, and all assignments are equally valid from their respective perspectives. There is no observer-independent fact about the quantum state of a system. Reality, in this picture, is fundamentally relational. This connects to Rovelli's work on quantum gravity, where he has argued that space, time, and matter may all be fundamentally relational rather than absolute. Things exist only in relation to other things. There is no absolute frame, no God's eye view from which all facts can be simultaneously read off. This is a radical departure from the classical picture of the universe, and it may be exactly what quantum mechanics is trying to tell us. The quantum information perspective has also been enormously productive technologically. Quantum computing exploits superposition to represent and process exponentially large amounts of information simultaneously. A classical bit can be either 0 or 1. A quantum bit, called a qubit, can be in a superposition of 0 and 1 simultaneously. A system of 100 qubits can simultaneously represent 2 to the power of 100 different numbers, more numbers than there are atoms in the observable universe. A quantum computer operating on all these states simultaneously can solve certain problems exponentially faster than any classical computer. This is not magic, and it does not mean quantum computers are faster than classical computers at everything. For most tasks, classical computers remain superior. But for specific problems, quantum computers have a provable advantage that scales with the size of the problem. The factoring of large integers, which underlies the security of much of modern internet encryption, can in principle be performed exponentially faster on a quantum computer using an algorithm called Shor's algorithm, discovered in 1994. The implications for cryptography, both constructive and destructive, are significant. Quantum key distribution uses the quantum mechanical impossibility of measuring a quantum system without disturbing it to create cryptographic keys that cannot be intercepted without detection. If an eavesdropper attempts to read the quantum signals carrying the key. The act of measurement inevitably disturbs the quantum states and reveals the eavesdropper's presence to the communicating parties. This is not a clever engineering trick. It is a direct consequence of the measurement postulate of quantum mechanics. Security here is guaranteed by physics, not by computational difficulty. Quantum sensing exploits another consequence of quantum mechanics: the extreme sensitivity of quantum states to perturbations from the environment. Atomic clocks, which are the most precise timekeepers ever built, work by using the quantum mechanical energy levels of atoms as frequency references. The best atomic clocks today, based on optical transitions in neutral atoms or trapped ions, are so precise that they would neither gain nor lose a second over billions of years. These clocks have been used to test general relativity at the level of centimeters of height difference, confirming that time runs slightly faster at higher elevations, exactly as Einstein's theory predicts. Quantum mechanics and general relativity, working together at the level of the most precise instruments humans have ever built, agree. Magnetometers, based on quantum mechanical spin states, can detect magnetic fields billions of times weaker than the Earth's field. This sensitivity has applications in medical imaging, navigation, and the detection of underground structures. Gravitational sensors based on atom interferometry, which is essentially a quantum mechanical version of the double-slit experiment using atoms instead of photons, can measure local variations in the gravitational field with extraordinary precision. These instruments have been proposed for fundamental physics experiments, including searches for dark matter and tests of the equivalence principle. Dark matter is itself connected to quantum physics in deep ways. Observations of galaxies, galaxy clusters, and the cosmic microwave background all point to the existence of matter that does not interact with light. This invisible matter, dark matter, appears to make up approximately 27% of the total energy content of the universe, compared to about 5% for ordinary visible matter. What dark matter is at the particle physics level is unknown. Leading candidates include particles called weakly interacting massive particles, or WIMPs, axions, sterile neutrinos, and primordial black holes, among others. Each of these is a quantum mechanical entity, and the search for dark matter is partly a quantum physics problem. If dark matter consists of axions, extremely light particles originally proposed to solve a different problem in particle physics called the strong CP problem, then the dark matter of the universe is a quantum field whose oscillations permeate all of space. Detecting it would require instruments sensitive to the tiny quantum oscillations of this field in the laboratory. Several experiments around the world are pursuing this goal using superconducting quantum circuits and high-quality microwave cavities to search for the minute signatures of axion-photon conversion in strong magnetic fields. The overlap between quantum physics and cosmology is not limited to dark matter. The large-scale structure of the universe, the web of galaxies and galaxy clusters and voids that fills the observable cosmos, is thought to have originated from quantum fluctuations in the early universe. During a period of extremely rapid expansion called inflation, which is hypothesized to have occurred a fraction of a second after the Big Bang, quantum fluctuations in the energy field driving the expansion were stretched to cosmological scales and became the seeds of all structure we see today. The patterns we observe in the cosmic microwave background, the faint afterglow of the Big Bang, contain the statistical imprint of these primordial quantum fluctuations. In this picture, the quantum world and the cosmological world are not separate domains. The large-scale architecture of the universe is a magnified imprint of quantum events that occurred in the first instance of cosmic history. Quantum mechanics did not just determine the structure of atoms and molecules, it determined the structure of the universe itself. This observation raises deep questions. If the universe began in a quantum state, then the measurement problem The question of what causes wave function collapse and why we observe one outcome rather than many is not just a laboratory puzzle. It is a puzzle about the origin and history of the universe. Why does the universe have a definite history at all, if quantum mechanics says that all possible outcomes of quantum events exist in superposition? Why is there one cosmos rather than a superposition of all possible cosmoses? The many worlds interpretation offers one answer. All possible histories do exist, and we inhabit one branch. The Copenhagen interpretation sidesteps the question by restricting quantum mechanics to the domain of laboratory experiments with defined measurement contexts. Other interpretations give other answers. None is fully satisfying, and the question of what quantum mechanics means for cosmology remains wide open. There are physicists who argue that the discomfort we feel about quantum mechanics stems from trying to apply our intuitions about mid-scale, everyday reality to domains where those intuitions simply do not apply. Humans evolved to navigate a world of objects with definite positions and predictable trajectories. The neural machinery that enables us to think about the world is tuned to that scale. It is not surprising that we struggle to form intuitions about a domain where position is not always defined, where objects can be in two places at once, where measurement creates rather than reveals. Our intuitions are not tools designed for that job. This does not mean we cannot understand quantum mechanics. We can. The mathematics is clear, and its predictions are unambiguous. What we cannot easily do is visualize quantum reality in terms of familiar images. Every visualization of a quantum state is, at some level, a metaphor, because the quantum state lives in a mathematical space, Hilbert space, that has no spatial analog in ordinary experience. The wave function of two particles lives not in ordinary three-dimensional space, but in a six-dimensional configuration space. For a system of many particles, the wave function lives in a space of mind-boggling dimensionality. There is no intuitive picture that captures all of this. The mathematics is the physics. This is a genuine epistemological shift. In Newtonian mechanics, the equations correspond to something visualizable, objects moving through space. In quantum mechanics, the equations correspond to probability amplitudes evolving in an abstract mathematical space. The question of what this abstract structure represents in terms of concrete physical reality is precisely the interpretation problem, and it has no agreed answer. What we can say with confidence is that this abstract structure is real in the pragmatic sense. It makes predictions that match experiment. Every application of quantum mechanics, from semiconductor design to MRI scanning to laser technology to nuclear medicine, depends on taking the quantum mechanical formalism seriously as a description of the world. A theory that does not correspond to anything real would not generate this cascade of accurate applications. Whatever quantum mechanics is pointing at, it is pointing at something genuinely there. The history of physics suggests that our concepts of reality must expand to accommodate new experimental discoveries rather than the other way around. Before quantum mechanics, reality meant classical objects in classical space. After quantum mechanics, that picture was shown to be an approximation, valid in a certain limit but not fundamental. Future discoveries may require similarly radical expansions of concept. Perhaps the notions of space and time will turn out to be emergent, approximate features of a deeper quantum reality. Perhaps the distinction between observer and observed will dissolve at a more fundamental level of description. Perhaps properties and relationships will turn out to be more fundamental than objects. These are not idle speculations. They are directions actively being explored by researchers at the frontiers of theoretical physics, quantum gravity, quantum information, and the foundations of quantum mechanics. The questions are hard, and progress is slow, but progress is happening. What remains is a picture of the universe that is, at its deepest accessible level, profoundly unlike our everyday experience of it. Particles are not tiny marbles. Fields are not invisible fluids. Measurement is not passive observation. Probability is not ignorance of hidden facts. Non-locality is not a violation of physics, but a feature of it. And reality, if that word is to mean anything in quantum physics, must be understood as something richer, stranger, and more subtle than the common-sense picture that served science well for 3 centuries before the 20th. The greatest scientists who have grappled with these questions, Bohr, Einstein, Heisenberg, Schrödinger, Dirac, Feynman, Bell, Wheeler, and those working today, have not been diminished by the strangeness of quantum mechanics. They have been invigorated by it. The strangeness is not a sign that the theory is wrong. It is a sign that the theory is reaching beyond the familiar into territory where human intuition was never equipped to venture alone. Mathematics, experiment, and rigorous reasoning have taken us to this frontier. They will take us further. That is, perhaps, the most important message of quantum mechanics. Not that the universe is strange, though it is, but that it is knowable. Careful experiment can reveal the structure of reality even when that structure defies all intuition. Questions that seemed hopelessly philosophical have received experimental answers. Properties that seemed obviously pre-existing have been shown not to exist before measurement. Non-locality that seemed obviously impossible has been confirmed in the laboratory. The universe has not hidden itself from our inquiry. It has answered every question we have managed to ask, and the answers have been consistent, precise, and genuinely surprising. That is the scientific enterprise at its best. Not the confirmation of what we expected, but the discovery of what we did not imagine. Quantum mechanics is the deepest and most productive example of that process in the history of science, and it is not finished. To go deeper into what quantum mechanics means, it is worth examining one particular set of experimental results more closely, because they represent perhaps the clearest window we have into the genuine strangeness of quantum reality. These are the experiments on quantum erasing, which extend the logic of the delayed choice experiments into territory that challenges even the most careful intuitions. In a quantum eraser experiment, photons are sent toward a double slit, but before they reach the detector, they are passed through a device that produces pairs of entangled photons. One of these, called the signal photon, continues toward the double-slit screen. The other, called the idler photon, goes in a different direction and is detected separately. The key is this: if the idler photon is detected in a way that contains information about which slit the signal photon went through, the signal photon shows no interference pattern. It behaves like a particle with a definite path. But if the measurement of the idler photon is made in a way that destroys the which path information, and if the results are post-selected so that only signal photons whose paired idler photons were measured in this information-erasing way are counted, then the interference pattern reappears in the signal photons. What makes the quantum eraser experiment genuinely disorienting is that the idler photon can be measured after the signal photon has already hit the detector. The result registered by the signal photon, whether it contributes to an interference pattern or not, seems to depend on what measurement will be made on the idler photon in the future. The future choice about whether to erase the which path information appears to reach back and influence the past behavior of the signal photon. This is not actual backward causation. No information can be sent into the past using this effect. The interference pattern in the signal photons only becomes visible through post-selection, which requires classical communication of the idler photon results, and that communication cannot go faster than light. But the quantum mechanical description of events is genuinely non-classical in a way that the word non-local only partially captures. The quantum correlations between the signal and idler photons persist across time as well as space. The past behavior of the signal photon is not fully determined independently of the future measurement on its entangled partner. Wheeler was fond of a thought experiment he called the participatory universe, and the quantum eraser provides something like a concrete experimental instance of the logic he had in mind. The observer's choice of what to measure, even after the fact, participates in determining what physically happened. The universe, at the quantum level, does not have a complete and definite history independently of the measurements that are made about it. This does not mean the universe needs conscious observers to exist. It means something more subtle and more profound, that at the quantum level, the concept of a definite physical history, independent of any reference to measurements or interactions, may simply not apply. Quantum events have definite outcomes relative to a measurement context. They do not necessarily have definite outcomes in some absolute observer-independent sense. And the experiments confirm this repeatedly with extraordinary precision. One concept that has gained increasing attention in recent years, particularly in the context of quantum gravity, is the idea that spacetime itself might be emergent from quantum entanglement. The physicist Juan Maldacena proposed in 1997 what has become known as the AD-CFT correspondence, a mathematical duality between a theory of quantum gravity in a curved spacetime and a quantum field theory without gravity on the boundary of that spacetime. This is a remarkable result. It says that one theory is exactly equivalent to a very different theory, one with gravity and one without, one in a higher dimensional spacetime and one on a lower dimensional boundary. In the technical language, the two theories are dual to each other. One of the profound implications of this duality, explored extensively in the years following Maldacena's proposal, is that geometric properties of the gravitational spacetime, including its connectivity and even its dimensionality, seem to be related to entanglement properties of the boundary quantum field theory. In particular, there is a mathematical relationship known as the Ryu-Takayanagi formula between the entanglement entropy of a region in the boundary theory and the area of a corresponding surface in the bulk gravitational spacetime. This suggests that spacetime geometry is, in some deep sense, built from entanglement. Geometry is entanglement. Space is woven from quantum correlations. This is a hypothesis, not an established fact. The AD-CFT correspondence is a mathematical result, but we do not live in an anti-de Sitter spacetime. Our universe has a positive cosmological constant, not a negative one. Whether the ideas developed in the AD-CFT context apply to our universe remains an open question. But the fact that a consistent theory of quantum gravity can be constructed in which spacetime itself appears to emerge from quantum entanglement is a major result. It suggests that the deepest connection between quantum mechanics and the structure of the universe may be even more intimate than previously imagined. If spacetime is emergent from entanglement, then the non-locality of quantum mechanics takes on a new meaning. Non-locality is not a feature of quantum mechanics that is awkwardly grafted onto a pre-existing spacetime. It may be the other way around. Spacetime is the emergent structure that arises from the quantum correlations between degrees of freedom, and what we call locality is an approximate, emergent feature that holds at macroscopic scales but breaks down at the fundamental level. This line of thinking is sometimes described using the phrase space is not fundamental. The idea is that the three spatial dimensions and one time dimension we experience are not the basic ingredients of reality, but rather high-level structures that emerge from a more fundamental quantum substrate. The analogy sometimes used is temperature. Temperature is a real and measurable feature of physical systems, but it is not fundamental. It emerges from the collective behavior of many molecules in motion. Space and time, in this speculative but increasingly explored picture, might be similar, real and measurable at our scale, but not fundamental at the Planck scale. The question of whether time is fundamental is particularly interesting in the context of quantum gravity. In quantum mechanics, time plays a special role. It is the parameter with respect to which quantum states evolve. But in general relativity, time is not a separate background. It is part of the spacetime geometry, which is dynamical and affected by the matter within it. When you attempt to combine the two theories, this conflict over the nature of time becomes acute. One of the most striking features of the Wheeler-DeWitt equation, a proposed equation for the quantum state of the universe, is that it has no time parameter. The wave function of the universe, in this framework, does not evolve in time. Time must emerge from the correlations within the quantum state of the universe itself. How exactly time emerges from a timeless quantum state is an active research question. One proposal, associated with the work of Don Page and William Wouters in 1983, suggests that time is relational. There is no absolute time, but clocks and the systems they measure become correlated in the quantum state of the universe, in a way that gives rise to the appearance of time evolution. Recent experiments with entangled photons have simulated this mechanism and confirmed that it is internally consistent. A photon that is entangled with a reference clock appears to evolve in time from the perspective of an internal observer, while appearing static to an external observer who has no access to the clock. This is a small-scale laboratory simulation of a profound cosmological idea, but it illustrates the power of quantum information methods for exploring foundational questions. By carefully engineering quantum states and measurements, physicists can study in the laboratory the mechanisms that may underlie the emergence of time itself. Returning to more immediately practical territory, the technology of quantum coherence is advancing rapidly. Quantum computers capable of outperforming classical computers on specific tasks, a property called quantum advantage, have been demonstrated on several occasions. Google claimed quantum advantage in 2019 using a superconducting quantum processor. IBM, Google, and a growing number of other companies and research groups are competing to build increasingly large and increasingly capable quantum computers. The challenges are formidable. Quantum states decohere rapidly when they interact with the environment, and errors in quantum computations are frequent and must be corrected. Quantum error correction is itself a fascinating application of quantum principles. You cannot copy an unknown quantum state, a result known as the no-cloning theorem, which is a direct consequence of the linearity of quantum mechanics. This means that the classical method of error correction, making redundant copies of the information and checking them against each other, cannot be directly applied to quantum information. But quantum error correcting codes exist, which spread the quantum information across many entangled qubits, in such a way that errors on individual qubits can be detected and corrected without measuring the encoded information itself. These codes are extraordinarily clever constructions. They exploit entanglement to protect against decoherence in a way that has no classical analog. Implementing quantum error correction at the scale needed for large-scale fault-tolerant quantum computing is one of the major engineering challenges of our time. Current quantum processors are called noisy, intermediate-scale quantum devices, operating in a regime where errors are too frequent for large-scale computations, but where quantum effects are clearly present and can be exploited for limited tasks. The path from these devices to fully fault-tolerant quantum computers requires order-of-magnitude improvements in qubit coherence times, gate fidelities, and the number of physical qubits per logical qubit. Researchers around the world are working on all these fronts simultaneously. The materials and physical systems used to implement qubits are diverse. Superconducting circuits operating at temperatures close to absolute zero, where quantum effects dominate, are used by many of the leading groups. Trapped ions, individual charged atoms held in place by electromagnetic fields, offer extremely long coherence times and high-fidelity gates. Photonic systems use individual photons as qubits, which have the advantage of traveling naturally at the speed of light for quantum communication. Silicon-based systems using either electron spin or nuclear spin of individual atoms implanted in silicon, offer the potential of leveraging the massive existing infrastructure of the semiconductor industry. Topological qubits, based on exotic quantum states that are inherently protected against certain types of error by topological properties of the material, are a longer-term research direction with potentially significant advantages for fault tolerance. Each of these approaches has strengths and weaknesses, and it is not yet clear which will prove most useful for large-scale quantum computing. The competition and diversity of approaches are healthy signs of an active and rapidly evolving field. Quantum networks, which would link quantum computers and quantum sensors through quantum communication channels, are also being developed. A quantum network would not simply transmit classical information encoded in quantum states. It would distribute entanglement, allowing quantum processors at different locations to share quantum resources and perform computations collaboratively in ways impossible with classical networks. The long-term vision is a quantum internet, a global network that enables applications including unconditionally secure cryptography, distributed quantum computing, and quantum-enhanced sensing, with baselines extending across continents or even to satellites in orbit. Practical quantum communication over long distances faces the challenge of loss. Photons carrying quantum information are absorbed by optical fibers, and the quantum no-cloning theorem prevents the straightforward amplification used in classical communication networks. Quantum repeaters, devices that can extend the range of quantum communication by establishing entanglement over shorter segments and then linking them together, are a major research focus. Several demonstrations of entanglement distribution over distances of hundreds of kilometers have been achieved using both fiber and free space optical links, including experiments involving satellites. China has deployed a quantum communication satellite called Mikius, which has been used to demonstrate quantum key distribution between ground stations thousands of kilometers apart and to distribute entangled photon pairs across intercontinental distances. These demonstrations are milestones in the development of practical quantum communication, though the technology is still far from being cost-effective for widespread deployment. All of this technological activity is motivated at the deepest level by the quantum mechanical properties of matter, superposition, entanglement, and the fundamental role of measurement. Understanding these properties well enough to exploit them technically requires understanding quantum mechanics at a fundamental level. And understanding quantum mechanics at a fundamental level keeps leading back to the philosophical and interpretational questions we have been discussing. The conceptual questions and the technological questions are not separate. They inform each other. Advances in quantum computing have led to new insights into quantum error correction, quantum entanglement, and the quantum to classical transition. Experiments designed to test fundamental interpretational questions about quantum mechanics have led to new quantum communication protocols. The boundary between pure science and applied science is, in this domain, unusually porous. This is worth emphasizing because there is sometimes a temptation to regard foundational questions about the interpretation of quantum mechanics as purely academic, disconnected from practical applications. The history of quantum physics refutes this sharply. The quantum mechanics that was first developed in the 1920s, driven entirely by theoretical curiosity and puzzling experimental results with no obvious application, gave rise within a few decades to the transistor, the laser, MRI scanners, solar cells, LED lights, and the entire infrastructure of modern electronics and photonics. These technologies collectively underpin the modern economy and have transformed human civilization. The quantum information revolution that is beginning now, again driven partly by foundational curiosity about what quantum mechanics means and what it allows, may prove equally transformative. Quantum computers able to simulate molecular systems at the quantum mechanical level will enable the design of new materials and pharmaceuticals with precision impossible using classical methods. Quantum sensors of unprecedented sensitivity will enable new forms of medical imaging, geological surveying, and fundamental physics experiments. Quantum communication networks will provide security guarantees grounded in physics rather than computational hardness. What the next century of quantum physics will bring cannot be predicted. The century that just passed was full of surprises. The discovery of quantum mechanics itself, the development of quantum field theory, the confirmation of antimatter, the unification of the electromagnetic and weak nuclear forces, the standard model of particle physics, the confirmation of quantum entanglement and non-locality, the invention of quantum computing and quantum cryptography. Each of these was surprising. Each transformed our understanding of the universe. The surprises ahead will be equally unexpected, and they will begin, as they always have, with someone asking a question that seems too basic to bother with, and then discovering that the question is deeper than anyone imagined. The quantum world is real. It is the substrate of everything. Every object you have ever touched, every light you have ever seen, every signal your nervous system has ever transmitted is made of quantum systems obeying quantum rules. The everyday world is a coarse-grained average over the quantum world, an average that hides the underlying strangeness behind the comfortable familiarity of classical behavior. But the strangeness is always there, beneath the surface, and it is the most fundamental truth about the physical universe that we have ever discovered. If you have followed all of this through the wave function and the measurement problem, through superposition and entanglement and non-locality, through the interpretational debates and the experimental tests and the technological applications, then you have engaged with some of the deepest questions in science. These questions are not closed, they are open, actively debated, and at the frontier of current research. The answers, when they come, will matter. Liking and subscribing keeps this kind of content coming. These topics deserve careful treatment, and there is always another layer to explore. The quantum world does not offer the comfort of certainty. It offers something better, the discovery that the universe is deeper, stranger, and more astonishing than we were able to imagine before we looked closely enough to see it clearly. And the looking is not finished. There is one more dimension of quantum mechanics that deserves careful attention, and it concerns the relationship between quantum physics and the concept of information itself. In the 20th century, two great theories of information emerged almost simultaneously with quantum mechanics. Claude Shannon's information theory, developed in the 1940s, gave a precise mathematical definition of information and established the fundamental limits of communication and data compression. Alan Turing's theory of computation, developed around the same time, formalized what it means to compute and established the limits of what any computing machine can accomplish. These theories treated information and computation in entirely classical terms. But when quantum mechanics is applied to information and computation, something new and extraordinary emerges. The physicist John Archibald Wheeler, who contributed so much to our understanding of quantum measurement and black holes, spent the final decades of his career developing a perspective he summarized in the phrase, "it from bit." His idea was that information is not just a useful description of physical reality. Information is more fundamental than matter or energy. Physical reality, in this view, arises from information. Every particle, every field, every force is ultimately an answer to a yes or no question, a bit of information. The universe is, at its core, an information processing system. Wheeler's it from bit program was speculative, but it influenced a generation of physicists and computer scientists who took seriously the possibility that information could be the fundamental substrate of reality. This influenced the development of quantum information theory, which showed that quantum mechanics and information theory are not merely analogous, but deeply unified. Quantum mechanics is fundamentally a theory about how information can be stored, processed, and communicated. The distinctive features of quantum mechanics, superposition, entanglement, the uncertainty principle, the no-cloning theorem, are all, in this view, statements about the nature of quantum information. The no-cloning theorem is a particularly striking example. In classical computing, copying information is trivially easy. You can make as many copies of a file as you like. In quantum mechanics, copying an unknown quantum state is impossible. You cannot take an arbitrary qubit, a quantum bit, in an unknown state, and produce two qubits both in that same state without destroying the original. This is not a technological limitation. It is a mathematical theorem derived directly from the linearity of quantum mechanics. Its implications are profound. It means that quantum information cannot be copied and distributed the way classical information can. It provides a physical basis for quantum cryptography. Any attempt to eavesdrop on a quantum communication channel necessarily disturbs the quantum states being communicated and can be detected. And it means that quantum information is, in a sense, more precious than classical information. Each quantum bit is unique and irreproducible. Related to the no-cloning theorem is the no-deleting theorem. Quantum information cannot be destroyed either, in the sense that the full quantum information content of a closed system is always preserved. This connects to a deep puzzle in physics. What happens to the quantum information stored in matter that falls into a black hole? Stephen Hawking showed in 1974 that black holes are not truly black. They emit thermal radiation, now called Hawking radiation, due to quantum effects near the event horizon. This radiation carries energy away from the black hole, causing it to slowly evaporate over astronomical timescales. For a stellar mass black hole, the evaporation time is so long that it exceeds the current age of the universe by many orders of magnitude. For a tiny primordial black hole, it could be shorter, but the endpoint is the same. The black hole eventually disappears. The problem, which has come to be known as the black hole information paradox, is this. Hawking radiation appears to be perfectly thermal, meaning it carries no information about what fell into the black hole. If this is correct, then information is irreversibly lost when matter falls into a black hole. But quantum mechanics, in its standard formulation, is information preserving. The laws of quantum mechanics are reversible. If you know the quantum state of a closed system at one time, you can, in principle, reconstruct the quantum state at any earlier time. Information cannot be destroyed. These two principles, black hole thermodynamics and quantum mechanics, appear to be in direct conflict. This conflict is the black hole information paradox, and it has been one of the central puzzles of theoretical physics for 50 years. Most physicists now believe that information is not truly lost in black holes, that Hawking radiation must carry subtle correlations, encoding the quantum information of what fell in a way that is not apparent in Hawking's original calculation. But how exactly this information escapes from behind the event horizon is not understood. The resolution likely requires a complete theory of quantum gravity that we do not yet have. Recent developments, including the study of what are called islands in quantum gravity and the connection between entanglement entropy and black hole geometry through results like the Page curve calculation, suggest that quantum information arguments can constrain and even determine aspects of black hole evaporation that could not be calculated by any other means. These results are tentative and mathematically complex, but they represent real progress on a problem that had seemed completely intractable. The black hole information paradox is not just a technical puzzle. It touches on the most fundamental questions about the laws of physics. If information can be lost, then quantum mechanics as currently formulated is wrong. If information cannot be lost, then something in our understanding of black holes and spacetime must be radically revised. Either way, something important and new will have to be understood. The connection between black holes and quantum information also extends to a concept called quantum complexity. In quantum mechanics, the complexity of a quantum state can be measured by how many elementary quantum operations are required to produce it from a simple reference state. Recent work by physicists, including Leonard Susskind, has proposed that certain geometric properties of black holes, in particular the growth of a region inside the event horizon called the Einstein-Rosen bridge or wormhole, correspond to the quantum complexity of the black hole's quantum state. This conjecture, called complexity equals action, or more specifically, complexity equals volume, or complexity equals action, depending on the precise formulation, proposes a deep and surprising connection between spacetime geometry and quantum information complexity. If correct, it would mean that the interior of black holes is in some sense a physical representation of computational complexity. These ideas are at the extreme frontier of theoretical physics. They are speculative, technically demanding, and their physical interpretation is debated. But they represent an extraordinary convergence of ideas from quantum mechanics, general relativity, information theory, and computation. Researchers are discovering that these apparently separate disciplines are different aspects of a single underlying structure that we are only beginning to understand. The tools being developed to study quantum gravity and black hole information are largely the tools of quantum information theory, entanglement, entropy, quantum error correction, quantum complexity. And the insights flowing from these tools are not just relevant to exotic objects like black holes. They are shedding light on the nature of quantum mechanics itself, on what entanglement really means, on why the laws of quantum mechanics take the form they do, and on what a complete and consistent theory of quantum reality might look like. There is also a growing research program concerned with the foundations of quantum mechanics from the perspective of operational theories. Instead of asking what quantum mechanics means, researchers in this program ask what features of quantum mechanics are necessary given a set of physical principles, and what alternative theories are possible if those principles are weakened or modified. This approach, called Reconstructing Quantum Mechanics from Physical Principles, has led to several remarkable results. Lucian Hardy showed in 2001 that quantum mechanics can be derived from 5 simple axioms, 4 of which are reasonable and classical, and one of which is a specific quantum postulate about the relationship between the number of degrees of freedom and the dimension of the state space. Other researchers have derived quantum mechanics from principles like the impossibility of sending signals faster than light, the impossibility of distinguishing non-orthogonal states, and constraints on how information can be compressed and transmitted. These derivations show that quantum mechanics is not arbitrary. It is the unique theory consistent with certain operational principles about information processing. It is, in a specific technical sense, the simplest theory that can describe systems with the measured statistical properties of quantum experiments. This is a remarkable result. It suggests that quantum mechanics is not just the theory we happen to have, because that is what experiments revealed, but the theory we must have given certain very general requirements about information and measurement. The strangeness of quantum mechanics is not gratuitous. It is the minimum strangeness compatible with certain fundamental operational requirements. Understanding which physical principles force quantum mechanics to have the form it does helps clarify what is genuinely fundamental about it and what might change in a future theory. If quantum mechanics is the unique theory compatible with certain principles, then any future theory that preserves those principles must reproduce quantum mechanics in the appropriate limit. This constrains what quantum gravity or any other extension of quantum mechanics can look like. The relationship between quantum mechanics and thermodynamics is another deep and active area of research. Thermodynamics is the science of heat, energy, and entropy. It was developed in the 19th century, before quantum mechanics, but quantum mechanics is necessary to give it a complete and consistent foundation. In particular, the origin of the second law of thermodynamics, The law that entropy never decreases in an isolated system has long been a puzzle. Classical mechanics is time reversible, so in principle any macroscopic process should be reversible. Yet we never observe entropy decreasing spontaneously. Glasses do not unbreak. Hot coffee does not get hotter by extracting heat from the room. The arrow of time is real and irreversible. Quantum mechanics adds new dimensions to this puzzle. Quantum evolution is also time reversible in principle. The Schrödinger equation evolves quantum states in a perfectly reversible way. Yet quantum measurements produce definite outcomes from superpositions, which appears to be an irreversible process. The connection between quantum measurement, decoherence, and the emergence of thermodynamic irreversibility from reversible microscopic laws is an active research area with both fundamental and practical implications. Recent work in quantum thermodynamics, applying quantum information methods to thermodynamics, has revealed surprising connections. The Landauer principle, which says that erasing information requires a minimum thermodynamic cost equal to temperature times Boltzmann's constant times the logarithm of 2, connecting information theory to thermodynamics in a fundamental way, has been extended and refined in the quantum regime. Maxwell's demon, a thought experiment in which an intelligent being appears to violate the second law by sorting molecules, has been analyzed quantum mechanically, revealing that information erasure is the source of the entropy cost that saves the second law. The boundary between information theory and thermodynamics, it turns out, is not just blurred. They are fundamentally the same subject. All of these research threads, quantum gravity, quantum information, quantum computing, quantum thermodynamics, foundations of quantum mechanics, represent a single vast enterprise of understanding. They are converging on a picture of reality in which information is central, in which the distinction between physical systems and information about those systems is not sharp, in which entanglement is not merely a quirk, but a structural feature of reality at the deepest level, and in which the concepts of space, time, and matter may all be emergent from a more fundamental quantum substrate. Whether this picture is correct, we do not yet know, but the coherence of the picture, the way ideas from such different domains are converging on similar conclusions, is itself significant. It suggests that we may be approaching a genuine conceptual revolution comparable to the one that produced quantum mechanics a century ago. The founders of quantum mechanics were not trying to produce a strange theory. They were trying to explain experimental results that could not be explained any other way. The strangeness was forced on them by the data. Future physicists will similarly be forced to wherever the data leads, and the data may well lead somewhere stranger than quantum mechanics, if that is possible to imagine. The scientific attitude toward this prospect is not anxiety, but curiosity. The universe has given us, with quantum mechanics, the most precise and powerful physical theory in history. It has shown us that reality is far richer and stranger than we imagined, and it has demonstrated, unambiguously, that careful experimentation can reveal truths about nature that no amount of pure reasoning would ever have led us to predict. The universe is more generous with its secrets than it sometimes appears. It yields them to those who ask precise enough questions in precise enough ways. That is the deepest lesson of quantum mechanics. Ask the right question with sufficient care and precision, and the universe will answer. The answer may not be what you expected. It may not be what you wanted, but it will be true, and it will be extraordinary. The work continues. To bring all of this into a single coherent perspective, it is worth asking what a scientifically honest summary of the situation looks like at the beginning of the 21st century. Not what we hope or what we fear, but what the evidence actually establishes and where the genuine uncertainties lie. What quantum mechanics has established beyond any serious scientific doubt is this: the universe is not locally realistic. Properties of quantum systems are not always defined before they are measured. Distant quantum systems can be correlated in ways that cannot be explained by any mechanism involving only local interactions. The randomness in quantum measurement outcomes is not a consequence of ignorance of hidden variables. These are experimental facts, not interpretations or philosophies, established through hundreds of independent experiments by researchers at institutions around the world over the course of nearly a century. What quantum mechanics has also established is that the standard model of particle physics, the quantum field theoretic description of the fundamental particles and forces, is extraordinarily accurate. It accounts for all known phenomena at the subatomic scale with a precision that no other physical theory has come close to matching. The Higgs boson, predicted by the Standard Model in the 1960s and discovered at the Large Hadron Collider at CERN in 2012, was the final piece of this framework to be confirmed experimentally. The Standard Model works. It is one of the greatest intellectual achievements in human history. What is not established is the correct interpretation of quantum mechanics. Whether the wave function is a real physical object or a calculational tool, whether all possible outcomes of quantum measurements occur in parallel universes, whether quantum randomness is fundamental or emergent from deeper deterministic processes, and whether consciousness plays any role in measurement, these are open questions on which physicists and philosophers disagree, and on which no experiment has yet decisively ruled. What is also not established is a satisfactory theory of quantum gravity. General relativity and quantum mechanics are both extraordinarily successful theories, but they are not yet unified into a single, coherent framework that works at all scales. At the Planck scale, which is roughly 10 to the negative 35 meters, about 100 billion times smaller than a proton, neither theory is expected to give correct predictions. What happens at these scales is unknown. String theory and loop quantum gravity are the most developed candidates, but neither has been confirmed experimentally. What is also unknown is the nature of dark matter and dark energy. Dark matter makes up about 27% of the universe's energy content. Dark energy, the mysterious force driving the accelerating expansion of the universe, makes up about 68%. Ordinary matter, the stuff we can see and touch and make experiments with, is about 5% of the total. We do not know what dark matter is. We do not know what dark energy is. These are not small gaps in our knowledge. They are enormous and central. The discovery of dark energy, announced in 1998 based on observations of distant supernovae, was one of the most surprising results in the history of cosmology. The universe is not only expanding, as Edwin Hubble had established in the 1920s, the expansion is accelerating. Something is pushing galaxies apart with increasing force as time goes on. This something is parameterized in Einstein's equations by the cosmological constant, a term he originally introduced and then abandoned, calling it his greatest blunder. It turned out not to be a blunder at all, but the value of the cosmological constant that observations require is so small compared to what quantum field theory naively predicts that it represents one of the deepest puzzles in theoretical physics. Quantum field theory predicts that the vacuum of empty space should be filled with enormous quantum fluctuations carrying a huge energy density. The observed cosmological constant is smaller than this prediction by roughly 120 orders of magnitude. Reconciling these two numbers is one of the unsolved problems of theoretical physics. This discrepancy, known as the cosmological constant problem, may require new physics beyond both general relativity and the standard model of particle physics. It may require a deeper understanding of the quantum vacuum, the ground state of quantum fields, or it may require a new understanding of how quantum field theory and gravity are related that goes beyond anything we currently have. It is a problem at the intersection of quantum mechanics and cosmology, and its resolution will likely require progress on multiple fronts simultaneously. The very early universe, the first tiny fractions of a second after the Big Bang, is a domain where quantum gravity effects are important, and our understanding is incomplete. Inflationary cosmology, which proposes that the universe underwent an extremely rapid expansion in its first instant, successfully explains several features of the observed universe: its large-scale homogeneity, its spatial flatness, and the statistical properties of the density fluctuations that seeded all subsequent structure. But the mechanism of inflation, the specific quantum field responsible for driving it, and the details of how it began and ended are not established. There are hundreds of viable inflationary models, and distinguishing between them requires measurements that have not yet been made. One of the key predictions of inflation that has been partially tested is the generation of primordial gravitational waves, ripples in spacetime produced by quantum fluctuations during inflation and stretched to cosmological scales. Detecting these primordial gravitational waves in the polarization pattern of the cosmic microwave background would provide direct evidence of quantum gravity effects in the early universe, and could discriminate between inflationary models. Several experiments are searching for this signal. As of the current state of scientific knowledge, it has not yet been detected, but the search continues. Gravitational waves themselves were detected directly for the first time in 2015 by the LIGO detector, confirming a prediction of general relativity that had been made a century earlier. The signal came from the merger of two black holes, each many times more massive than the Sun, occurring about 1.3 billion light-years away. The merger released more energy in gravitational waves in a fraction of a second than the Sun will emit as light in its entire 10 billion-year lifetime. And yet the effect on the LIGO mirrors was a displacement 1,000 times smaller than the diameter of a proton. Detecting this required one of the most precise measurements ever made, exploiting quantum optics and quantum noise reduction techniques to push the sensitivity of laser interferometers below the standard quantum limit. The detection of gravitational waves opened a new window on the universe. Gravitational wave astronomy has since observed dozens of black hole mergers, neutron star mergers, and mixed black hole neutron star mergers. The simultaneous detection of gravitational waves and light from a neutron star merger in 2017 enabled tests of whether gravitational waves travel at the speed of light, confirming it to extraordinary precision, and provided a new method for measuring the expansion rate of the universe. Gravitational wave astronomy is now a mature field contributing to our understanding of compact objects, nuclear physics, and cosmology. But the most scientifically consequential aspect of gravitational wave detection, in the context of quantum physics, is what it may eventually enable. Future gravitational wave detectors, more sensitive than LIGO, may be able to detect gravitational waves from the early universe, including the primordial gravitational wave background left by inflation. This would be a direct observation of quantum effects from the Planck era, the closest we could possibly get to observing quantum gravity with astronomical instruments. Space-based detectors like LISA, the Laser Interferometer Space Antenna, proposed for launch in the 1930s, will be sensitive to gravitational waves at frequencies inaccessible to ground-based detectors, and will open another new observational window. All of this represents a profound transformation in how we do physics. For most of human history, our picture of the universe was based entirely on electromagnetic radiation, visible light, and then radio waves, infrared, ultraviolet, X-rays, and gamma rays. Gravitational waves are a completely different channel. They pass through matter almost without interaction. They carry information from environments that would be opaque to any electromagnetic signal, including the cores of neutron stars, the interiors of black holes, and the hot plasma of the early universe. Multi-messenger astronomy, combining gravitational wave observations with electromagnetic and neutrino observations, is giving us a richer and more complete picture of astrophysical events than any single channel could provide. Neutrino astronomy is another window. Neutrinos are produced in enormous quantities in the cores of massive stars during supernova explosions, in the centers of active galaxies and in other energetic astrophysical environments. They interact so weakly with matter that they pass through the entire Earth essentially without interaction, which makes them difficult to detect but also allows them to bring information from dense, opaque environments where photons could not escape. The IceCube neutrino detector, an array of sensors embedded in a cubic kilometer of Antarctic ice, has detected high-energy neutrinos from astrophysical sources, opening yet another new observational window on the universe. The combination of these new observational channels, gravitational waves, high-energy neutrinos, cosmic rays, and the full electromagnetic spectrum, with increasingly powerful theoretical tools from quantum mechanics, general relativity, and computational physics, is enabling a new era of astrophysics. The universe is more accessible to observation than at any previous point in human history, and the rate of discovery is correspondingly high. Within this broad landscape of discovery, the quantum mechanical nature of reality remains the foundational framework. Every instrument we use exploits quantum mechanical properties of matter, whether the quantum transitions in atomic clocks, the quantum optical properties of laser light, the superconducting properties that enable sensitive quantum sensors, or the quantum detectors that count individual photons. The quantum world is not separate from observational astronomy. It is the basis of everything we observe with. And the questions that quantum mechanics raises about the nature of measurement, the reality of the wave function, the interpretation of probability, the relationship between observer and observed, are not separate from questions about the universe. They are questions about the universe. The deepest questions in cosmology and the deepest questions in quantum foundations are, it is increasingly clear, the same questions asked from different vantage points. This convergence is one of the most exciting features of contemporary theoretical physics. The tools of quantum information developed to understand quantum computers and quantum communication are being applied to black holes and cosmology. The mathematics of quantum error correction is showing up in discussions of quantum gravity and the holographic principle. The concept of entanglement entropy, developed to characterize quantum information in condensed matter systems, is providing new insights into the geometry of spacetime. These are not superficial analogies. They are deep structural connections that suggest the various domains of physics are more unified than they appear on the surface. The unification that physicists have sought for decades, a theory that reconciles quantum mechanics with general relativity, may not come from finding a quantum-field theory of gravity in the traditional sense. It may come from a more radical reconceptualization in which spacetime and matter both emerge from a more fundamental quantum information structure. The pieces of that reconceptualization are being assembled slowly and carefully by researchers around the world. What we know with certainty is this: the universe, at every scale we have probed, is quantum mechanical. Atoms are quantum, molecules are quantum, chemical bonds are quantum. The nuclei of atoms are quantum. The forces between particles are mediated by quantum fields. The early universe was quantum. The structure of spacetime at the Planck scale, whatever that structure turns out to be, is quantum. There is no refuge from quantum mechanics. It goes all the way down. What that means for our picture of reality, for our understanding of space and time and matter and causality and the nature of the physical world, is still being worked out. It will keep being worked out for decades and centuries. The project of understanding quantum reality is not approaching its conclusion. It is still near its beginning. The questions that motivated the founders of quantum mechanics, what is matter really made of? How do particles behave at the smallest scales? Why does measurement play such a special role in physical theory? Are still alive. They have grown richer and more intricate as we have learned more. They will grow richer still as future generations of physicists, armed with better instruments, more powerful theories, and deeper mathematical tools, push the inquiry further. That is the nature of genuine science. It does not converge on a final answer and stop. It generates better and more precise questions as it goes. Every answer reveals new depth. Every experiment raises new puzzles. The horizon recedes as fast as we approach it, which means that the universe is, in a very real sense, inexhaustible. This inexhaustibility is not a failure, it is a feature. It means that the enterprise of understanding the universe is not approaching its end, it is accelerating. The rate at which new knowledge is being generated, in quantum physics, in cosmology, in particle physics, in condensed matter physics, in quantum biology, is higher than at any previous point in history. The universe has more to show us, and we are getting better at looking. Quantum mechanics has taught us, above all, that the universe does not match our expectations. It matches the evidence. The expectation that particles have definite positions and momenta before measurement, wrong. The expectation that distant particles cannot be instantaneously correlated, wrong. The expectation that the laws of physics are deterministic, wrong, or at least not established. The expectation that the fundamental structure of the universe should be intuitive to beings who evolved to navigate a mid-scale world of trees and rivers and other animals, not a well-supported expectation. What the universe owes us is nothing. What it has given us, through the patient and careful practice of scientific inquiry, is everything we know. And what we know, even now, is enough to fill a lifetime of wonder. The work continues.